Hello, we are Team EJ04, and we made a PC-controlled DC power supply with data logging capabilities for our Junior Design 2 course. I am Alex Carroll. My teammates were Luis Ahumada Medina and Robert Cleaver. Our goals for this project were to make a power supply that could supply 2 to 14 volts over 2 channels with a peak current of 1.5 amps. In addition to the power delivery goals, we had the additional goals of making our power supply IP43 rated, recording the output of both channels, and being controllable by a computer. Throughout the course of our project, we faced many challenges. The most notable of these challenges were designing and implementing the voltage regulator circuit, an accurate current and voltage sensor, and a method for recording the data that is both readable and accessible. Some notable achievements are recording voltage and current values to a micro SD card, 3D printing an enclosure that is IP43 rated, designing a voltage regulator, and being able to measure what voltage and current are being outputted by the channels. One consideration for improving the project in the future would be adding a wireless control option to the power supply. Another improvement would be adding the option to power our power supply using a wall outlet. We will begin by discussing the system overview, then breaking down each subsystem, and wrap up by elaborating on future developments and our achievements. Our system provides the user with 4 outputs: the 2 power channels, an LCD display, and a data file. To operate, our system needs to be powered by a USB port and by an 18-volt DC supply. Additionally, there are 4 control buttons along with a power button on the front of our enclosure. If the user chooses to plug the system into a computer via the USB, it allows them to control the power supply using their computer. We broke our project down into 6 blocks. These blocks are the voltage regulator, current and voltage sensor, microcontroller, input converter, data logging and display, and the enclosure. Each of us was responsible for 2 of these blocks. Lewis was responsible for the enclosure block and the data logging block. Robert was responsible for the current and voltage sensor block and the input converter block, and I was responsible for the voltage regulator and microcontroller block. Even though each of us were responsible for 2 blocks, we all collaborated together to help each other complete our blocks. The voltage regulator block takes the 18-volt power supply and transforms it into the output voltage specified by the user. The main components of our voltage regulator block were a digital potentiometer and a voltage regulator. Initially, we tried to use a digital potentiometer that was only rated for low voltage. Due to this, our circuit used amplifiers to both step up and down the voltage to supply the feedback pin of the voltage regulator with the correct voltage without overvolting the potentiometer. Unfortunately, when we built the circuit after we simulated it, the circuit did not work. We tried to troubleshoot our circuit, but were unable to make it functional. We pivoted to using an MCP45HV51, which is a high voltage digital potentiometer. The downside of using this potentiometer is that it is controlled by I2C instead of basic up-down pins, which meant more code needed to be written for the microcontroller. Using the high voltage potentiometer meant that the amplifiers could be cut out of our circuit. We created a custom PCB for this block, which made soldering the circuit easier because of the small size of the potentiometer. To keep our PCB as small and therefore as cheap as possible, we used 2 identical PCBs with each channel needing its own PCB. This also allowed for more flexibility in the layout of our enclosure. Before the outputs of the voltage regulator block reach the user, it needs to go through the current and voltage sensors so we can make the readings necessary for displaying and logging the data. The current and voltage sensors measure the voltage and current of both channels and send these measurements to the microcontroller so it can be displayed and, if specified, by the user saved. The voltage and current sensors ended up being independent from one another. The voltage sensor is in parallel with the output. It is constructed of 2 resistors and a potentiometer. The resistors divide the voltage by 1/3, so it is always below the maximum of 5 volts specified by the microcontroller. The potentiometer allowed us to adjust for difference in between resistors, giving us more precise measurements. The microcontroller used this input to calculate the voltage. The current sensor is in series with the output. We used a ACS712 as a current sensor, which outputs an analog signal that changes in magnitude based on the current going through it. This signal is also sent to the microcontroller so it can be turned into the current value. Each channel needed its own current and voltage sensor, which meant we needed to use 4 analog to digital channels on the microcontroller. The microcontroller we used was a Nucleo L476RG. We chose to use the Nucleo for a couple of different reasons. A large amount of I/O was something we wanted from a microcontroller, as we knew we would need many ports for the LCD input buttons and voltage and current sensors. In addition, we did not know what other I/O we would need, so using the Nucleo left us with lots of room to add devices. We also wanted something with a large amount of storage because our initial plans to store the recorded data on the board. The Nucleo was the only microcontroller we used in our system, which means it handled all the computation, data processing, and controls of the system. With the addition of the high voltage potentiometers, we needed to use the I2C bus. When we transitioned to using the micro SD card for storage, this also increased the amount of I/O our system required. Fortunately, we were able to supply all of the interfaces we ended up needing due to the expansive options the Nucleo provides.
The input converter block tells the system what to do based on the user's input. Originally, we planned to have the power supply take button inputs and computer inputs to control the channel voltages. But unfortunately, we were not able to get the communication between the computer and the microcontroller to work. For that reason, our power supply is only able to be controlled using buttons. To make it easier to wire and set up the buttons, we designed a PCB dedicated for buttons. The PCB was designed to have 2 buttons on them. This allowed us to arrange the buttons in different locations around the power supply. One of the button PCBs were dedicated for incrementing and decrementing the voltages, while the other PCB was used for changing the channel that is being adjusted and initiating the data logging. The data logging in the display block is what displays voltage and current values to the local LCD display, and when the user presses a designated button, 30 seconds worth of voltage and current values will be saved to the microSD card as a text file. The values themselves are coming from the voltage and current sensor block, and the LCD is connected to a potentiometer and the microcontroller. The turnable potentiometer adjusts the contrast of the LCD so that the user can control visibility of the text, while the microcontroller is what is used to control what is displayed on the LCD. To record values to the micro SD card, we used a micro SD card module, where the module works by receiving commands and data from the microcontroller over SPI protocol. Originally, we planned to use the Nucleo microcontroller to save files to the local computer, but we found out that the microcontroller did not have a file system, so we could not create and access files on the computer. So we decided to shift to a ESP8266, a wireless capable microcontroller, where we plan to save the values to a Google spreadsheet. We were able to save values to a Google spreadsheet, but we were running into problems where we couldn't communicate between the 2 microcontrollers, and so values couldn't be sent in between them, and the values themselves for the current and voltage were not being updated. So we ended up shifting our focus to a micro SD card module. We were actually able to get the communication to work, and we were able to update the current voltage values. The enclosure block is the physical structure of the power supply. This was done using computer-aided design software Fusion and was 3D printed. When thinking about the design of the enclosure, there were a few constraints that needed to be accounted for. First, the enclosure needed to have enough space to house all the components needed by the power supply, but it cannot be larger than what is able to be printed by 3D printers. Second, the enclosure had to have openings for the interfaces that were needed by the power supply. This included the button, the channel connectors, power connectors, potentiometer, LCD display, micro SD slots, and the mini USB opening. Third, there needs to be a way to open and close the enclosure. Otherwise, we can't put things inside the enclosure. Finally, the enclosure has to meet IP43 rating. This means that the enclosure must not have unplugged openings that are greater than 1 millimeters and still be operational after being sprayed with water less than 60 degrees from vertical. Our first enclosure was designed to have dimensions of 230 by 150 by 88 millimeters and made out of PLA material. We chose PLA because it is durable and water resistant. The inside of the enclosure could be accessed by unscrewing the top using a screwdriver. Unfortunately, the enclosure was designed and printed before the data logging was implemented using microSD card module and before the button PCB was made. As a result, there was no microSD card slot, and the distance between the buttons did not match how the buttons were placed on the PCB. So we needed to make a new enclosure. The second enclosure, designed to have the openings for the SD card module and the correct spacing for the buttons. We also designed the lid to not be screwed on, but to be sliding. And so this made it faster to open the enclosure and made it so that we didn't need tools in order to open the enclosure. The opening for the various interfaces were also refined to be more exact. This would make sure that there was no longer any 1 millimeter or larger unplugged openings and save them into a text file. The most notable accomplishments we achieved were designing a voltage regulator and button PCB, implementing an accurate voltage and current sensor, saving voltage and current values to a microSD card, and designing an enclosure that meets IP43 ratings. In the future, we would like to develop an app that can wirelessly control the power supply so that the user can view the channel voltage and the current, change the voltage of the channels, and save the voltage and current data to a local device. This could be done by adding another microcontroller that has wireless capabilities in order to send and receive data to and from the app, possibly using Bluetooth or Wi-Fi. This would make the power supply easier to use and record values. Another possible improvement would be changing the power supply so that it can be powered using a standard wall outlet. This could be done by implementing a rectifier to convert the wall power to a voltage that the power supply can use. This would allow the power supply to work anywhere where there is a standard wall outlet.